Okay, now I'll give you some idea about how to prepare the final exam for Chem 2. Again, Chem 2 final exam, we will use the ACS standard exam, include some from Chem 1. So you need to review all quiz from Chem 1 class. Okay. First, about molecular geometry. Table 10.2 and 10.4, very important. Read these two tables at least 3 times. Try to understand them. For example, use table. You can judge what is molecular geometry. Sulfur hexane fluoride, so octahedral, and sulfur tetrafluoride, seesaw, also called distorted tetrahedral. So read this table carefully. Read the table 10.2. The example list here is A, B. This is model A, B, 4, E. E is empty, no atom there, just long pair electron. Table 10.4 also very important. It also tells angle between bonds. For example, sp2 hybridization. 3 bond, right? So 3 orbitals could form 3 bonds. And this 3 bonds in the plane 360, so equal divided by 120. So 120 degree. The example is CH3, CO double bond, and CH3. So this bond 120 degree. This also 120 degree. Because this carbon's hybridization is sp2, 3 bond, 1, 2, this 3. Double bond is 1 is sigma bond, 1 is pi bond. Okay, so 1 pi bond added there becomes double bond. Skeleton is single bond, single bond, single bond, 120 degree. Okay. Number 2 I can think about is the shape of an orbital. With a set of quantum numbers. You may not notice. Which quantum number determines the shape of the orbital? Air. N is principal quantum number. Determines distance of the electron from nucleus. The larger n, the further of electron from nucleus. N1 is here 1, closest to the nucleus. N2 is here 2, N3 is here 3. Air determines the shape of the orbital. So if air is 0, this is S orbital. S orbital looks like a ball. Shape looks like a ball. If air equal to 1, this is P orbital. The shape looks like this. Either this X or this Y or Z axis. Anyways, X, Y, and Z. Right, this is 3 dimension in the space. Shape looks like lobe or 2 balls stick together. Okay. So electron travel on the surface of this lobe. If air equal to 2, that is d orbital. D orbital, we have 5 d orbitals, 5 orientation. P, 3 orientations, X, Y, and Z. D, 5 orientations. The d orbital shape looks like this. So anyway, air value determines the shape of the orbital, while ML is the orientation, so not related to the shape, only orientation. Also, ML's actual value not directly related to which orientation. Just tell you ML, you have several different values represent several different orientation. Third, what I can think about is rate law for reaction. Let's say A react with B. Produce product P. May tell you sets of experimental results. Start with different A and B concentration. A0 means initial A concentration. B0 is the initial B concentration. V0 is the initial reaction rate. Initial rate. Chart 1 start with A0 is 1, B0 is 0.5. Initial rate is 1.5 times 10 to the negative 3 molar per second. Chart 2 start with A0, A is 1, and B0 also 1. The initial rate is 6 times 10 to the negative 3. Chart 3, A start with 3, B start with 0.5. Initial rate is 4.5 times 10 to the 3rd power. Then what is initial rate law? So rate law will look like this. K rate constant. A concentration raised to X's power. B concentration raised to Y's power. Then what is X? What is Y and Z? Y no Z because only 2 reactants. So now if we compare chart 1 with chart 2, initial A concentration is exactly the same, but the B double, right? B, chart 2, B started with 1. Chart 1 is only 0.5. And this reaction rate is 4 times faster. 1.5 becomes 6. So if we compare V2, This initial rate, let's label 0 in upper corner. So V20 over V10, then according to this rate law, should be A times A concentration is 1, right? Raised to X. B concentration is 0.5. No, this is char 2. So use 1. Char 2, B is 1. And char now use 1. This V1 is char 1. So A concentration, by the way, the K is really constant, is the same. It's char, because we run experiment at the same temperature. Then K should be same. So char 1, A concentration also 1. 1.0, 1.01 is the same. Okay. Char 1, B concentration is 0.5, and you find A concentration exactly the same. Char 1, char 2, right? B concentration doubled. So this 1 divided by 0.5 is 2. Both is the Y's power. Since V2 is 6 times 10 to the 3rd power, and V1 is 1.5 times 10 to the 3rd power, and this power is exactly the same. So 6 divided by 1.5 is 4. So 2 to Y's power equals to 4. What does this mean? Y is 2. Second power to B. And if we compare char 1 with char 3, so B concentration exactly the same. A concentration 3 times higher. So V30 over V10. So K times A concentration is 3 to X to the power. B is 0.5 to Y's power. K is the same. Char 1, A concentration is 1 to X to the power. B concentration is 0.5 to Y's power. And you find this time B concentration exactly the same. Be cancelled. Left over only A's concentration. So K also cancelled. Similar here, K cancelled. So only left over A concentration 3 times higher. So 3 divided by 1 is 1. And both is X to the power. While the V3 is 4.5 times 10 to the 3rd power. And V1 is 1.5 times 10 to the 3rd power. So this is a 3. So 3 X to the power equal to 3. So X equals to 1. So now your rate law should be K times A raised to 1's power and B raised to 2nd power. So A is first order, B is 2nd order. Overall, 1 plus 2 is 3rd order. This is about kinetics of a chemical reaction. And next one I can think about is about rate constant at 2 different temperatures. They're linked with activation energy with temperature. Log K2 over K1 equal to EA divided by R times inverse of T1 minus inverse of T2. So be careful the order. If you put K2 over K1, here is T1, T2. Okay. The order is opposite. So from this equation, we could have 2 different problem solving. So if we know K1, K2 at 2 different temperatures, T1 and T2, so we can calculate activation energy EA. Or if we know EA and K1 and T1, then we can calculate K2 at T2. Of course, K2 at T2 means T2 is a known value. Next one, still about kinetics. This is integrate the rate law. For first order reaction, integrate the rate law is natural log of A over A0 equal to negative K times T. K is the rate constant. T is time in second. A0 is the initial concentration of reactant. A is the reactant concentration at the time T. So use this integrate the rate law, we can calculate A at the time T. If we know initial A concentration and K. If we know initial A concentration together with K, then we can calculate the A concentration at any temperature T, at any time T. Of course, initial concentration and the concentration at any time T must in same unit. So most cases use molar concentration, so mole per liter. Next, I can think about is about catalyst. Catalyst in chemistry is a substance that can speed up a reaction. Why the catalyst can speed up the reaction? By reducing activation energy, EA. Catalyst itself during the reaction, no net change. Only speed up the reaction. Catalyst itself, no net change. That means you can recycle it, you can keep use it. Next, about the pH of a weak acid, let's say 0.5 molar acetic acid, and I tell you Ka is 1.77 times 10 to the negative fifth power. How to calculate the pH? So weak acid partially break down into hydrogen ion and acetate ion. So initially 0.5. If break down X, will generate X hydrogen and X of acetate. Then your Ka equal to hydrogen concentration times acetate concentration divided by HAC, acetic acid concentration. So X times X divided by 0.5 minus X equal to 1.77 times 10 to the negative fifth power. Since this Ka is a pretty small number, 10 to the negative fifth power, and this concentration also not very small. So I would say this dissociated part X compared with zero point 0.5 is very small. So 0.5 minus X is still approximate as 0.5. So this equation can be simplified as x squared divided by 0.5 approximately equal to 1.77 times 10 to the negative fifth power. Then your x will be approximately square root of 0.5 times 1.77 times 10 to the negative fifth power. Then this is the hydrogen ion concentration. Then the pH will be negative log of this hydrogen ion concentration you calculate from here. Okay, that's all I can think about how to prepare a final exam for Chem 2. Okay. Good luck to everybody.